Hello everyone. So welcome to lecture number 4. So we have been discussing the consecutive reaction, and in this lecture we will continue to do so. Last time we discussed about uh, 3 different cases and the possible graphical representations. So for consecutive reaction A going to B going to C, we have the rate constant K1 and K2, and last time we have derived the integrated rate equation C3 is equal to something like this. And then I explained that there are 3 different scenarios possible, that is K1 and K2 are comparable and K1 is much greater than K2, and those 2 scenarios we have already discussed in terms of graph plots. And in this case we are going to discuss case number 3 where K1 is much greater than K2. And I told you that this scenario would lead us to a very special and interesting scenario. So we will take a look at that. But before, we must understand that mathematically, when K1 is negligible, the entire kinetics is governed by the first step, which is the rate determining step. Okay, and the corresponding equation gets simplified into something like this. So now we are going to draw the graph plot. So let's draw the time axis over here, and this is the concentration axis. Okay, and we start with the first, that is A. Okay, so since K1 is very small, the substance starts to decay slowly. All right, so something like that, a slow but steady decay. And then once A starts to decay, obviously the B starts to form like that. But one problem is, since K2 is so much greater than K1, as soon as B, so this is my B over here, okay, so as soon as B is formed, immediately it gets converted into C. So with continuing decay of A, there is an initial lag period of C because it takes some time for B to degrade into C. But once the C starts to generate, it will pick up gradually and steadily, and then it will continue to get formed. And likewise, A would decay like this. But what would happen for B? There would be some initial buildup of the concentration B, but as the time lapses, whatever amount of B is getting produced, it would be decaying into C. So therefore, the effective concentration of B would fall, but very slowly, something like that. So there would be a period from here to the completion of the reaction. So in this part, you see that as if the concentration of B is almost constant. So here we can write that dB dt is equal to 0, or dC to dt is equal to 0. This is the same thing, okay? dC to dt, according to our definition over here. So in this scenario, if you look at the graph once again, you will get 2 things. That the concentration of B would appear to constant very soon after the reaction started, and the time period where the concentration of B seems to be constant, we call that scenario as steady state. Okay, and this is the concentration of C. This is the decay. This is how it decays. So therefore, in any consecutive reaction where A going to B going to C, where the first step is the rate constant of the first step is negligibly small, this gives to a situation called situation of steady state. Okay. Now, this has been a huge, there has been a huge implication of this concept of steady state, because we can apply an approximation. This is called a steady state approximation. So, what's that approximation? So, the approximation tells me that whenever we have an intermediate, so here V is an intermediate, okay? So whenever we have an intermediate, then on that intermediate, it is possible to apply the approximation of steady state. So that means what? Whenever we apply the concept of steady state, we can assume that the intermediate's concentration is not changing with time. And that concept would help us to solve many multi-step complex chemical kinetics. And what we have found that this steady state if we apply the steady state approximation, the experimental results tally pretty much with the theoretical treatment. That means the steady state approximation. So this is the graph plot of case number 3, and therefore what we are going to do now is we are going to revisit the consecutive reaction under the light of steady state approximation. Okay, so let's once again treat the consecutive reaction from a different angle. Okay, so if we revisit the consecutive reaction under steady state approximation, then what happens? So now let's see, B is the intermediate. So that means the steady state approximation can only be applied on B, or the concentration of it, that means C2. It can be applied with the reactant, or it can't be applied with the product. So if we write dC to dt, obviously this is K1C1 minus K2C2 that we have already seen before. Now under steady state approximation, we can write that this should be is equal to 0. Now if this is 0, or we can write that K2C2 is equal to K1C1 is equal to, so now the C1 can be represented as K1 C0 e to the power minus K1T, following the first order kinetics, and that we have already seen. So therefore, if we are interested on the integrated rate loss of C3 under steady state approximation, so we can start from dC3 dt. So dC3 dt is equal to nothing but K2C2, because this is the only way we can form C3. So therefore, we can immediately write K2C2 is equal to K1 C0 e to the power minus K1T. So therefore, if we integrate that equation, that means dC3 dt is equal to K1 C0 e to the power minus K1T. So if we integrate that, we definitely get C3 is equal to C0 1 minus e to the power minus K1T. And in fact, we get back the same equation that we have already found by applying this approximation, that is K1 much less than K2. So remember, in this treatment, we did not use the approximation earlier, but we directly applied the approximation, that is dC to dt is equal to 0, and we automatically arrived at this conclusion, that is K1 is much greater than K2. So this is a very easy and simple way to get the C3, isn't it? Okay, good. So before we move on to our next topic, let me just tell you, probably I forgot to explain last time, that under this case, when K1 is much less than K2, the graphical representation is something like this. So this is my C1, and this is my C2, and this is my C3. Okay. So you see that under this situation, the steady state is achieved right after the reaction has started. So that means within very few percentage propagation of the a very small percentage propagation of the reaction attains steady state. So thereafter, so if I go beyond this dotted line, the chemical kinetics will essentially appear that as if C1 is decaying. Okay, so C1 is decaying means it is essentially the first step. So as I explained you last time, that when K1 is much greater than K2, so the entire kinetics is dictated by the second step. So the graphical representation actually reflected that. And here also the graphical representation reflected that the chemical reaction is essentially governed by the first step. So in many practical application, we can apply the concept of steady state or steady state approximation. So that means we automatically assume that whenever we are having some intermediates, the intermediates is getting formed slowly. So that means the intermediate forming rate constant is small, and there could be many intermediates, and we can apply the approximation of steady state at each stage. Okay, so this is just an approximation, and experimentally, as I said, it has been found that this approximation holds very good. So it matches our theoretical calculation with the experimental one. So therefore, we would move to verify some real-life example of chemical kinetics where the concept of steady state approximation can be applied. So let's take a look on that. Okay, so welcome to one of the most classically studied free radical reaction. So that is the formation of hydrogen bromide gaseous from hydrogen gas and bromine gas, and this happens under photocatalysis. So this is a photochemical reaction. So that means a photon acts as a catalyst for this reaction. So we have to use the steady state approximation to find out the rate law. Okay. So now, before we go into the detail, let me tell you. So this reaction proceeds by 5 principal steps. So the first step, the bromine molecule gets dissociated into Br dot, which is a free radical. And then the Br dot reacts with H2 to get HBr. So HBr is the product, plus it again forms an H dot. Okay. And then H dot again reacts with the Br to the reactant and again forms HBr, which is the product, and again Br dot, the free radical. And then some of the HBr may react with the H dot to give back the reactant again plus Br dot. And finally, if the Br dots they fuse with one another, we form the Br2. That means we get back the reactant. So the salient features of this reaction, the number one, this is called a free radical chain reaction. So why the chain reaction? Because it, first of all, why free radical? Because it mediates through formation of the free radicals. And number two, why is it chain reaction? It is called chain reaction because it undergoes few repetitive sequence of the same reaction. So that means once that H dot once the Br dot is formed, so Br dot is helping to form HBr and generating H dot. And from this H dot, again we are getting HBr, and with formation of HBr we are having Br dot. Okay, so repetitively, cyclically, it goes back to H dot, Br dot, and again it helps to form new HBr molecule, and with new HBr molecule we have new H dot and Br dot, and it again, the reaction proceeds. So these 5 steps can be classified under different categories. So the first one, where we are first producing the Br dot, and for this we need photon as a stimulus. So we call this chain initiation. Okay, so this reaction is called chain initiation. And these two steps where the reaction propagates and we form HBr, so that is the main chain reaction actually. So this is called chain propagation. Okay, so here we only get product. And then the fourth step, you see, HBr is not formed, but it is forming H2, the reactant. So that means it's inhibiting the process of the reaction. So this is called chain inhibition. And the last step, where the Br dots, one of the main intermediates, are getting back to the reactant. So that means the reaction stops here because we are forming the reactant back. So this is called the chain termination. In fact, the reaction does not continue forever. It has to stop. And it stops via this mechanism by formation of the bromine molecule back. So these are the individual different types of steps. So now we are going to solve the chemical kinetics. Okay. But it's your job to verify that if we put the the steady state approximation correctly, then we are going to derive this expression, that is dHbr dt is equal to something like this. You see, it's a complicated expression, but we have to get to that final result. Then only we'll be able to understand, we'll be able to realize that we have understood how to apply the concept of steady state approximation. So therefore, to help you, I'm going to write the very first step. So here we have to find out dHbr dt. Okay. So how we can express dHbr dt? So the first step that we are going to write, the dHbr dt, how HBr is changing. So HBr is getting formed from the first step. So that is K2 multiplied by Br dot H2. Okay. Also plus, it is getting formed from the third step, that is K3 multiplied by H dot and Br2. And then it is getting vanished from the reaction by minus K4 multiplied by HBr multiplied by H dot. Okay. So this is the first initial step we can write, and from that we have to develop. So now look at that very carefully, that here we have the term Br dot, H dot, and here also H dot. So before we solve this kind of stepwise chain reaction, our initial job is to identify the intermediate species, because if we are going to apply the steady state approximation, we only have to apply for the intermediate, nothing else. So our duty to identify the intermediate. So what are the intermediates here? If we look at this, definitely if you look at the steps, the intermediates are only two things, two species, Br dot and H dot. So here we have Br dot, here we have H dot. So now we are going to apply the steady state approximation. So the steady state approximation means that we can write d Br dot dt is equal to d H dot dt is equal to 0. But before that, we have to find the expression for dBr dt, like I have found this one, and dH dot dt, and then setting that is equal to 0, you will form two different equations, and from those equations, if you solve that for H dot and Br dot, so these are two unknowns, you need two simultaneous equations. If you solve that, you got Br dot and H dot, and if you put those values over here, you are expected to get this one. Okay, so I want you to do this exercise. Okay, it's for your benefit, and this way you can only learn. But before we proceed to the next example, let me tell you that on what basis we are applying this dBr dot dt is equal to dH dot dt is equal to 0. Of course, this is steady state approximation. But remember, most important thing, in a multi-step chain reaction, we are not going to evaluate the individual K1, K2, K3, K4 values, because here we are in no position to identify that we can only apply steady state approximation because my K2 is less than the K3 or K4 is very less than K5. No, we are for applying steady state approximation, this kind of reaction, we don't go by the rate constants, but we go by only two considerations. What are those? Please remember. Number one, at any time, the concentration of the reactants are very small, means the concentration of the intermediates rather. So the concentration of intermediates are very small at any time, and also the concentration of the intermediates at the same time appear to be constant. So we can write d intermediate dt is equal to 0 at any time. So it's now your turn to solve it, and I'm sure you will get this. But remember, you have to get this expression exactly. Okay, so try it out. So now let's move on to another example of a free radical chain reaction. So another classical example of the free radical chain reaction is the formation of CaCl2 gas from chlorine gas and carbon monoxide gas. Okay, so the question is, you have to identify firstly the steps that are chain propagation, chain initiating step, and the chain termination step, and then you have to find what are the different types of intermediates. So pick the intermediate species from this reaction, and lastly prove that the following reaction follows a 3/2 order kinetics. Okay, so it's your job, you have to prove that this free radical chain reaction is governed by 3/2 of fractional order kinetics. So now, does it make sense? Because I remember at the very first lecture, we told that for multi-step reactions, the molecularity of the slowest step is the order. But here, see, there is no fractional molecularity, but still the order is coming to 3/2. And I told you at that time that exceptions occur in free radical chain reaction. And my friend, this is the exception. So free radical chain reaction, and the order is fractional, although it goes by multi-step, and none of the steps molecularity is 0 or fractional order. So if you are able to solve this problem successfully, then we assume that you have learned how to apply the concept of steady state approximation, and you may expect more problems like this in the form of tutorial, and also it may appear in the tests. Okay, so next we move on to our last type of simultaneous reaction. Remember, one is still left, that is called the parallel reaction. So the parallel reaction is defined where in a reaction that changes happen in more than one way. So here we are showing only two products. It can be more than two, can be three, but of course those instances are a bit rare. So let's concentrate on a species A that is simultaneously giving us both the products B and C. And these are all first order, unidirectional, that means irreversible, rate constant K1 and K2. So at time t is equal to 0, the concentration of A was the smaller case a, and the concentration of B was 0, and the concentration of C was 0. But at time t is equal to t, the remaining concentration of A is basically A minus X. Alright? But here is the catch, that at time t, the total concentration of B plus C should be is equal to X. Because whatever X is getting formed, it is distributed into B and C. So it's not like that B and C are individually X. So the summation of B and C is equal to X. Alright? So what we can write, that is the dx dt, that means the rate of appearance of the product, okay, is basically it is the summation of B and C. Okay, so we can write that dx dt is the rate of formation of both B and C. So now individually, if we write that, let's assume that dy dt is basically the rate of formation of B, and it is equal to, of course, k1 multiplied by a minus x at any time. And similarly, dz dt is equal to the rate of formation of the product C is equal to k2 a minus x at any time. So, of course, then dx dt would become is equal to dy dt plus dz dt. So this is equal to dy dt plus dz dt. And if that is so, we get that is equal to k1 plus k2 multiplied by a minus x. Alright. So now we have formed an equation, an easy looking one, that is dx dt is equal to k1 plus k2 multiplied by a minus x. So now we are going to integrate that over here. Okay, so let's clean the blackboard and write it. So we have rewritten that equation dx dt is equal to k1 plus k2 a minus x, and on transforming and on integrating and by putting the appropriate conditions, that is at time t is equal to 0, x was 0, then we can finally get that integrated rate law of a parallel reaction, something like this. So now we can plot a versus x versus t, and we can get the summation of k1 plus k2. But k1 and k2 are individually unknown, so from the graph plot we can know the summation. But to know that individual values, we need to have another equation. Okay, so how to frame the another equation to get the values of k1 and k2. So if you remember, if we take the ratio of dy dt over dz dt, then it will give us that k1 multiplied by a minus x and divided by k2 multiplied by a minus x. So these two cancel out, and we get a simple ratio of k1 divided by k2 is equal to m, say. So if we compare the two rates, there is the rate of formation, the ratio of the rate of formation of the product B by C, product C, would give us the ratio of the respective rate constant, that is K1 by K2. And from the rate of the the ratio of the two rates, we solve K1 and K2, and then enter equation is known, and we can predict X at any time t. So now we are going to look at an example. So the example we can think of is something like this. If we have a bromobenzene and we want to brominate this, okay? So if you want to brominate that bromobenzene, we can expect two products, okay? So one product is definitely this. One bromine gets into the ortho position plus HBr, and we also get parallelly another product where the bromine goes to the para position plus HBr. So we have an ortho substitution here and a para substitution here. So from this it goes parallel. Okay, so one rate constant can be K1 and another is K2, and the entire kinetics can be followed by this rate equation. All right. So we are almost done with the simultaneous reaction, but we are now going to study a little bit more complicated scenario where opposing reaction and consecutive reaction happen at the same time. So let's take a look at that, and once again that would give us a special scenario which can be applied later in practical cases. So let's take a look at that. Okay, so now we come to a little bit more complicated scenario for a simultaneous reaction. Now you see here, this reaction is a mixture of opposing reaction and a consecutive reaction. A plus B reversibly forms I, and I going to form the product P. So there's a possibility that I may form an equilibrium with A plus B, or it may not form an equilibrium. So now let's take a look at the different scenarios and different conditions that end up in forming whether an equilibrium or not. So we are interested in finding out dP dt. That means in what rate the product P is getting formed. So let's find out what is dP dt. So dP dt can be only formed by this single equation K3I. There is no other way it is possible that P can be formed. So therefore, we have to find out the concentration of I. That means this. So how to approach the problem? So from whatever concepts we have learned, we can clearly see that I is an intermediate because it is getting formed in situ and it does not appear either in the reactant side or in the product side. So it is formed in situ and gets consumed in situ. So therefore, we can apply the steady state approximation. So we write here applying steady state approximation. So let's find out what is di dt. So di dt is equal to K1 multiplied by A B minus K2I and then minus K3I. Okay, so therefore this gives me K1 A B minus I common K2 plus K3. Okay? Okay. So if under steady state approximation is applied, then this should be equal to 0. If this is equal to 0, we can try to evaluate the concentration of I as K1 multiplied by A B divided by K2 plus K3. Okay. So at this time point, we are now interested to evaluate dP dt. So we know that dP dt is equal to K3 multiplied by I. So here we are going to write dP dt is equal to K3 multiplied by K1 multiplied by A multiplied by B divided by K2 plus K3. Okay. So therefore, we have come down to a rate law for a situation like this by applying the steady state approximation. So now let's take a look at the scenario over here, that what are the different repercussions if we consider the different values or different limits of K1, K2 and K3. So let's take a look at this equation. So now what if we consider that in this equation K2 is much greater than K3. Okay. So if K3 is negligible with respect to K2, therefore this dP dt becomes is equal to K3 K1 divided by K2 multiplied by A multiplied by B is equal to, we can write it here, K3. Now what is K1 by K2? Okay. So if you look at this equation over here, so once we write once again this little section portion of the equation, K1 plus K2. So if we assume that there is an equilibrium that is established, so the chemical equilibrium constant can be represented as by K1 by K2. All right. And also this chemical equilibrium constant can be represented as concentration of product I at equilibrium divided by A multiplied by B. So therefore this becomes K3 multiplied by chemical equilibrium constant multiplied by A and multiplied by B. So that tells me what? So that tells me actually that if K2 is much greater than K3, or K2 is negligibly small compared to K3, so that means once the product is when K3 is negligibly small with respect to K2, so that means once the product intermediate is formed, instead of quickly decaying into the product, if it comes back to dissociate into the reactants A plus B, there is a chance of formation of equilibrium. So that part would come under equilibrium. And that condition therefore is called a condition of pre-equilibrium. Okay. So this pre-equilibrium can also be derived in this manner, that of course I have written it here. So the chemical equilibrium constant is equal to this, or if I want to find out the value of I, concentration of I, it becomes equal to the chemical equilibrium constant multiplied by A multiplied by B. Okay, so therefore if we put that value over here, dp dt, so once again dp dt is equal to K3 multiplied by I, so it will give me K3 multiplied by chemical equilibrium constant multiplied by A multiplied by B. Okay, so this is the same thing with this one. So these two are basically the same equation, and we can tell that this reaction is second order. This is governed by a second order kinetics, and there is a establishment of a pre-equilibrium. So mind that in actual equilibrium condition, these values are constants. I equilibrium, A equilibrium, B equilibrium. Again, we are using an approximation term. So this is not exactly constant. So that's why this is the word called pre-equilibrium. That means it approaches the equilibrium, almost there but not there. So it's an approximation method. And the approximation method gives me that it follows the second order kinetics. And this is pre-equilibrium condition is only established when K3 should be negligibly smaller than K2. So now let's discuss the another scenario. That is, what happens if this is just the opposite? That what happens if K2 is negligibly smaller than K3? Okay, so then what will happen? So from the equation here drawn at the left portion here, we can say that then dp dt become equal to, so K2 here is negligible, so we can neglect K2, and then K3 cancel out, and we get K1 multiplied by A multiplied by B. So this is basically, once again, It shows also the second order kinetics. Okay, but here you see only K1 appears, so that means the first step is the rate determining step. Okay, so we can infer that this step is the rate determining step. And since this is the rate determining step, single step molecularity is 2, order is 2, so it is governed by the second order kinetics. Okay, so what we understood that in a complex reaction like this, where there's a mixture of some opposing reaction as well as consecutive reaction, if certain condition is fulfilled, then an establishment of pre-equilibrium is possible, and then the reaction is not governed by the first step. And when that condition is not there and some other condition is fulfilled, then the reaction may be governed by the first step. But in all the cases, it follows a second order kinetics. So therefore, in a reaction like this, the exact mechanism will tell us that whether we should be using the approximation of pre-equilibrium or the approximation of the steady states. So therefore, in this lecture, we have learned about two approximations. One is the steady state approximation and another is the pre-equilibrium. So now why we are discussing this pre-equilibrium versus steady state approximation? Because these concepts would come back once again in homogeneous kinetics or homogeneous catalysis, where we will learn the mechanism of enzyme kinetics. Okay, so we will use these two concepts once again. So please do try to understand and remember that, because we will need that for our future application. So with this, we have covered a considerable amount, taking from the preliminaries of the chemical kinetics and the simultaneous reactions. And our next section is basically catalysis. So there we will learn homogeneous catalysis and heterogeneous catalysis. Before that, we will start with the Arrhenius equation, and we'll learn about the different factors that govern the rate constant. But at this point, we'll take a pause and we will try to visit or go through a series of tutorial lectures where we will address a few questions and answer to make ourselves familiar about the chemical kinetics. Okay, so we will follow some tutorial lectures next. So I hope you enjoyed. Stay put, stay safe. So I will see you in the next tutorial lecture, which will be tutorial 1. Till then, goodbye.